we're going to do is to use the same actuation voltage, which is almost the same case in MEMS switches. And what we found here is that increasing the thickness actually at a specific voltage will result in decreasing the injected charge density. This is a high frequency material. And it is really more clear in the case of low frequency material. You can find that the slope is really very high here. What about the decay? As you can see here, increasing the thickness actually results in decreasing the decay time constant. So this means if you have a specific actuation voltage and you have thinner dielectric and thicker one, the thicker will have less injected charge density and faster discharging process. That's why we say that thicker dielectric is better for reducing the charging in MEMS. People from our design, of course, will say no, because this would affect the C-on, C-off ratio, so we have to make a compromise between those. The second effect we have investigated actually is the effect of the deposition conditions, and as we mentioned at the beginning, we used two deposition recipes, low frequency and high frequency, and when we compared between them, we find a considerable difference actually. Then we also investigated the effect of the gas ratio, silane ammonia, and then the power and temperature. Now we are going to see only low frequency versus high frequency, then only the gas ratio. We characterize using Kelvin force microscopy thin film, FDC thin film, and then using also FTIR and XPS. Just to give you an idea about what happens when you change the deposition conditions, you can have a look for this figure, where we change it only the gas ratio, silane and ammonia ratio, the reactive gas ratio. Okay, at a specific voltage, and you can see it's completely changed surface potential, new surface potential. This is the 0.15, and this is the 0.8. So controlling the gas ratio actually results in changing the injected charge density considerably. Let's have a look first for the high frequency silicon nitride versus low frequency silicon nitride. You can see here from Kelvin per force microscopy that increasing in high frequency materials, the injected charge density is smaller than low frequency material at different thicknesses. This is the 400, this is a 300, 200, and so on. The blue one here is a high frequency. So high frequency has less injected charge density than low frequency. And this is also verified from the FDC and finally from the CDCT. What about the discharging? As you can see here is a high frequency has a smaller decay time constant than the low frequency for all the frequencies. Which means what? Which means the high frequency material has a smaller injected charge density, has faster discharging process comparing to low frequency silicon nitride. And when we wanted to understand what happens actually with these different materials, we did again FTIR and XPS, and we find clearly that the high frequency material is more silicon rich than the low frequency material. Yes, the difference is not really big, but still you can see that the difference between the high frequency and low frequency, which is actually confirmed also by FTIR, the hydrogen hadron over silicon hydrogen bond, which means higher silicon content means you have more defects, you have more distribution passes, so you have more leakage current, and this leakage current actually results in equilibrium at smaller surface charge. That's why we measure smaller surface charge with high frequencies than low frequency. The other important difference between high frequency and low frequency actually is the deposition power. Because people thinking about low frequency and high frequency as just changing the frequency mode of plasma. No, this is not right. You have everything different. Gas ratio is different, power is different, and the pressure is the pressure is different. If you look here at this, you find the deposition power in case of low frequency is 185 watt. For high frequency, it's only 20. A huge difference actually. This high power and low frequency makes a lot of disorder during the deposition and results in changing the defects concentration and distribution, which means you can trap more charge and then you can store them for longer time. The second important parameter we investigated actually is the effect of the gas ratio, where we change the gas ratio from 0.15 up to 0.8, then we measure the surface potential profile using Kelvin force microscope. You can see easily that the injected charge density is decreasing gradually from 0.15 to 0.45. Then when we go for 0.6 and 0.8, you have a sudden drop. The same is confirmed by the adhesive force. You have a gradual decay, then you have a sudden drop here when you go for 0.6 and 0.8. When we go for the decay, we find also the same. The decay time constant is decreasing when you increase the gas ratio, and then a sudden drop here at these 2 points. confirmed actually by the decay time constant. This is a logarithmic cascade, so you have to be careful about treating this graph, and the same stuff from the FDC. So what happens then with these different gas ratios? What happens is that what you can see here is increasing the gas ratio results in increasing the silicon content in the film. This is confirmed from XPS and from Fettier, from these bonds together. So again, as we mentioned, with high frequency, more silicon-rich film means higher leakage current. You have more redistribution patterns, which means you have the equilibrium at a smaller surface charge or a smaller charge. Because simply what you measure using Kelvin force microscopy is the equilibrium between two main mechanisms, which is the charging and the discharging. So because of the fast discharging process here, everything is collected by the bottom electrode, and only smaller charge are remaining at surface, which you can measure with Kelvin force microscopy. So based on these techniques, we have seen that we can optimize our electric deposition conditions to reduce the charging, and what we have used actually is very simple structure, bare electric film. We don't use MEMS devices. Now, what is the effect of the packaging environment? This is what the system we have used in Ohio State University, where we controlled actually three main parameters. We put the sample here inside the AFM chamber in a plexiglass, and then there's two inputs, dry air from a desiccant and the humid air from a water cooler. And the input actually is two environments, air and nitrogen, and then there's also filters. You can apply yes or no to use this filter or not. So what we can control from the system actually is the environment medium, which means air or nitrogen, the relative humidity using this picture, and finally the environment contaminants using these filters. Just to give you again an idea about what humidity do with your surface potential distribution, you can have a look for this surface, for this graph, where you find at very small humidity it is confined and higher potential, while here it is smaller but spreading over a larger area. And this actually explains the limitations in previous measurements. This is what we do actually here. You can find easily with humidity, the distribution of the charge is increasing, right, for different electric field. And US is decreasing with humidity. So what is the overall conclusion from here? The overall conclusion actually is the integral of the surface potential, where we find clear that the injected charge density is increasing with the relative humidity. Of course, it increases because of many reasons, including the effect of the absorbed water film when you increase the humidity, the surface charge, the neutralization also with the external medium, and so many other parameters. And for the decay, actually the US is decaying faster at higher humidity, as you can see here, which is verified for the time by the decay time constant. While the distribution of the charge over the surface actually goes very fast with higher humidity. So again, what is the conclusion? US is decaying fast, US is spreading very fast. The conclusion actually you can get easily from the integral with time, where you can find easily that the 40% is decaying very fast compared to the 0.02%. Which means what? Which means when you increase the humidity, your charge is dissipating or collected very fast. This means humidity is good for MOSFET switches. We will see the answer in a minute in the following slides. The other important point for the humidity actually is the surface charge. This is the background voltage, which we measure actually at different humidity, where no charging is there. We just measure the surface potential over non-charging area. You can see easily that we are measuring different background potential with humidity. Increasing with the potential, with the humidity means we have more surface charge with humidity. This actually could explain why we have faster lateral spreading over the surface. So what happens with humidity? With humidity you have larger injected charge density, you have faster discharging process, right? And then you have also faster lateral charge redistribution. Finally, you have more surface charge. This means what? This means the smaller humidity levels actually is better for MEMS switches, because simply what you have is a smaller injected charge density, so you have a smaller shift, and then this higher surface charge will make this spreading of the charge more uniform on the surface, increasing the effectiveness of the electrostatic force. Simply, this agrees with what we have in literature, where they find the shift of the activation voltage increases with humidity. What about about air versus nitrogen. Which packaging environment I should use? I should use nitrogen or air? So what we have done here is a comparison between air and nitrogen. You can see easily increasing, changing from air to nitrogen results in a smaller injected discharge density. You see here the air is filling the orange while nitrogen is still there. So the injected discharge density in nitrogen is smaller than air, while the decaying is faster in nitrogen than air. The other important point here is that the surface charge actually in air is higher than in nitrogen. Of course, this is due to many reasons. We explain this in details of the thesis, due to the gas discharge, due to different counterants, surface charge, the conductivity, and so on. This means what? This means in nitrogen we have a smaller injected discharge density, faster discharging process, smaller surface charge, which leads to the fact that nitrogen is better for process switches than air. This actually agrees with what the published data from IMEC, where they have shown that the lifetime in case of air is shorter with 100, factor of 100 than in case of nitrogen. While our techniques actually helps to understand what happens with different environments. The last thing we have done, I should go very fast for this, is a different gas purification where we use different filters. And as you can see here, that when we used the hydrocarbon filter with a nitrogen line, we have actually smaller injected discharge density because a smaller US and a smaller L maximum. The same issue for the hydrocarbon filter when we use it with air, while the effect in the case of nitrogen was higher. For the discharging process, as you can see here, using the hydrocarbon filter results in faster discharging process compared to air. Same conclusion we have seen using the oxygen filter with the nitrogen line, which means what? Which means using a well-purified environment, which means free from hydrocarbons and organic contaminants, reduces the injected discharge density and the discharging process. You might say the difference is not really big, the difference is small. I just say be careful, this is the results of 1 second discharge injection. Here, what we do is we inject pulses for only 1 second. In MEMS switches, you have injection for longer time. So this effect actually is expected to be more pronounced with real MEMS device. So any small effect you see here is magnified a lot for the real device. And we already investigated the effect of the charge injection time, but I'm not going to present it today. Finally, yes, the other important point here is the oxygen actually plays a very important role in the charging and discharging, and this was the reason actually before using the oxygen filters. The idea came from when we compared it between nitrogen and air, and we find nitrogen actually is decaying faster and have a smaller injected discharge density. The main difference between air and nitrogen composition actually is oxygen. That's why we have purchased this oxygen filter. We put it with a nitrogen line, and in spite that it is expected that the oxygen atoms with the nitrogen line is really small, it has this effect. So this means oxygen is really important. We have to be careful about that. Last thing I'm going to talk about is the different detection mechanisms in MEMS devices, where what we did, simply using again the force distance curve, is using the adhesion and the friction under different humidity levels, which means different meniscus force, and under different voltage, which means different electrostatic force. Simply here, we'll apply bias. We don't apply any bias between the tip and the sandal. And then the adhesive force, as you can see, is increasing with humidity, right? You might ask why all of this graph is empty, because we're going to see it will be filled by other stuff right now. While the water film thickness actually is increasing with the humidity, which explains the increase in the adhesive force with relative humidity. Due to, of course, the meniscus formation of all these issues. Then what we did is we applied the potential between poles. See what happens. This is with the applied bias, different biases you can see here, and this is adhesive force. You can see here we have 3 different samples, A, B, and C. A is dehydrated. We anneal the sample before the experiment. Then we make the experiment at very small humidity. Okay. Then for B, we'll also anneal before, and then measured at 60% humidity, very high humidity. So comparing between B and A, we can conclude easily the effect of the humidity, right? Then for C, what we had is we did not anneal the sample at all, but we measured it at 1% humidity, very small. So comparing A and C, we can conclude the effect of the annealing step. So there is a huge analysis behind this. The conclusion is this graph actually, because if we wanted to understand this in details, we need to measure the induced surface potential in the three cases. So what we did is we measured the surface potential based on force distance curve measurements. Then we plotted the effective bias. Here is the effective bias. This is the applied bias. The effective bias actually is the applied bias minus the measured surface potential using FDC, the technique we developed with FDC. And you can see here clearly from this figure the following. The adhesive force is increasing in the three cases with A, C, and B. That's fine. But if you look at the increasing rate here, you find smaller comparing to C and B. It is at the same effective bias, which means the same electrostatic force. We were expecting at the same electrostatic force to find the same adhesive force, which is not the case. So why is this difference comes from? We cannot say it is from humidity, because actually if you look at the previous curve, you will find that the slope is really small. The difference is really very small. So it is not humidity, it is not electrostatic force, because we have the same electrostatic force. There must be something else. When we did a survey for this, we find that the meniscus actually is formed under different mechanisms. The initial or the known mechanism is that when you touch the surface with no applied voltage, you have meniscus formation. When you apply a voltage, actually something happens where this water atoms is attracted to the tip or to the asperity of MEMS switches. The surface tension increases. And this means the volume of the water or the liquid surrounding the tip is increasing. So the force required to get rid of this water volume actually is increasing. This basically explains why we have this sudden increase in C and B. So in C and B, the dominant mechanism behind increasing the adhesive force is not meniscus formation, is not electrostatic field. It is actually the multi-physics coupling between both, which is the electric field induced in meniscus. And actually it was the first time to report this for MEMS devices. If we take these results and apply it for MEMS switches, we will find the following. For MEMS switch A, which was annealed and measured at low humidity, you have this. The near contacting asperity is almost the same. While for MEMS switch B and C, which was annealed and measured at higher humidity, or not annealed and measured at low humidity, you will find that the near contacting asperity will become a contacting asperity. And the semi-contacting asperity are now a full contacting asperity under the effect of field-induced meniscus. This actually explains what we have in literature where the lifetime of MEMS switches operated at larger humidity level is almost smaller than smaller humidity levels. People say it is a charging. No, it is not the charging. It is the electric field induced meniscus, which is actually induced by charging, which means you can eliminate it by reducing the humidity level or packaging your device in a dry environment. The other important point here is we understand now why when we anneal MEMS devices before packaging, the lifetime is increasing. It is not because of the charging. Actually, we have compared this data with the models for electric field meniscus, because actually there is a threshold voltage required to initiate this phenomena, and we calculated the induced surface potential in the three samples here, and then we compared it with this model and we verified this. It could happen with sample B and C and cannot happen with sample D. So we have to be careful when you talk about stiction. We have to be careful because the charging is not the only filler mechanism here. We should add this filler mechanism now to the table we presented at the beginning. So now it is 19 filler mechanisms. We don't know what's next. I came now to the conclusion, and as I mentioned in the beginning, we presented actually a complete package of novel characterization techniques, mainly nanoscale and macroscale, and we used it actually to study the charging in MEMS. We correlated between these techniques. These techniques actually is not for MEMS switches only. This is the message here. This is for any electrostatic MEMS device, where it could be applied in different ways to understand different phenomena, like the charging and stiction and so on, because the charging is not the only problem in MEMS switches. There's also other devices which suffer from the same stuff. The second point is we present a correlation between these techniques. We have seen that MEM capacitors and MEMS switches can lead to the same conclusion regarding the material properties. And this is a very interesting conclusion. Before, we were not able to see if it is possible or not. Now we know, but not using DCT, but using KPFM or FDC. Of course, DCT is good. I like it, but Kelvin force microscopy and FDC is much more good. Then, FDC actually has a lot of advantages compared to Kelvin force microscopy. FDC has the real MEMS device. You can measure higher potential, higher humidity, with accurate surface potential. So the message here, the first message from this series actually is, what we need to use is not a single characterization technique. We're not saying today this is the best, we have to use this. What we're saying is we use Kelvin force microscopy on the level of a single aspirated charging, integrated with force distance curve on area charging with meniscus formation, then DCT for the bulk properties. The integration between these characterization tools actually can give you an overview of what happens actually with your material. The other important message is you don't need to fabricate your MEMS device just to study the charging. If you give me 20 dielectrics today, I give you the list at the end of the day saying which one is good for MEMS. Okay? You don't need to fabricate the whole MEMS device. The second point is the stretched exponential equation is really a magical solution for such a study where it fits properly with everything. It fits with currents, potential, and adhesive force. We have seen thicker dielectric is better. Some people will not agree with this, but this is what we found. We found out that silicon material with more silicon content will have less charging. We find that if you want to have a good packaging environment to reduce the charging, you can use nitrogen at low humidity and using a very purified environment. We are not saying this because might be this is known, but we provide the explanation behind that. Finally, we have seen that there is a strong interaction between the tribological issues, adhesion and friction. By the way, we also studied friction, but I have not presented here, and the charging phenomena. We find electric field induced in meniscus is really a dominant stiction mechanism in MEMS switches. We need to add it now to the table as a new filler mechanism. And finally, this nanoscale and macroscale characterization shows a very good correlation with what we have from MEMS devices. And the most important point is it explains actually many several reported data from MEMS devices. What we can do next actually is still there is a lot to be done. First issue is that we need to make better correlation with MEMS switches. We have not compared the CV measurements, for example, with our own switches. We fortunately completed the fabrication of a complete library of MEMS switches just 2 weeks back. Now we have MEMS switches in labs here with different electric thickness, with different deposition conditions, with different power, gas ratio, and so on. And what we're going to do is to measure these switches and then to make a correlation between this and what we have. So we need to focus on this more. Then we can make a 2D and 3D study for the deposition conditions. We can change 2 parameters at the same time, 3 parameters at the same time, then determine the optimal deposition conditions. Then it's time now actually to apply these proposed techniques to different dielectric materials. I understand that might be some people say it is only silicon nitride, there is also other materials. Yes, we agree, but we have to decide from the beginning whether to go for single material, multiple characterization techniques, or multiple material, single characterization techniques. This is the way we have selected, but we believe it's time now to investigate other materials. Finally, atomic force microscopy family of characterization techniques is really very rich family. We investigated only 2 techniques, which is the Kelvin force microscopy and force distance curve. There is also the conductive atomic force microscopy, the tunneling atomic force microscopy, scanning resistance microscopy, scanning capacitance microscopy. We can investigate all of these issues to see it might be useful for our problem. The final message here is that the nanotribological and microtribological phenomena or the studies actually is required to understand what's happened with the interface of the switch, because the issue is not the charging only now, the issue is the charging, adhesion, and friction, and multiphysics coupling between them. This comes actually to the conclusion of the thesis, which is we have to think different actually, because MEMS failure is multiphysics problem. And if any, I always find this, if something has multi, the solution should have multi. So we have multidisciplinary analysis. And this makes the problem actually more and more complicated. So I'm done now with my technical talk, okay? I don't know if it is might be more than 45 minutes, I don't calculate. 40 minutes, perfect, okay. I think now it's time for a better talk than this technical stuff, which is the acknowledgement. This work actually has been done through many projects, European projects and French projects. Also Amicom was a starting point for this. Then, as you have seen, the work is really, as we mentioned, multidisciplinary from different scientific domains, nanoscale characterization, and solid-state physics, and nanotribology. And it is really logic that there is no a single person can do this alone. As far as I believe, this work would have been possible to be done unless we have all of this interesting collaboration between three main organizations. Here, LAS CNRS, and Ohio State University is a nano probe laboratory headed by Professor Bouchan, and the University of Athens solid-state physics headed by Professor Giorgio Bavagliano. I believe I was really very lucky to work with these three groups. So I'm really grateful to my advisors here in LAS, Professor Plana, Dr. Patrick Pons, and Fabio Picciuti for all this continuous support during making this work. Thank you very much for this. And I'm also really grateful to Professor Bouchan. I spent almost 1 year with him in the labs there at Ohio State University, where really, for me, was a very fantastic period where we interact with multiple people from different domains, material science, chemistry, physics, and so on. And this actually leads to all of this work related to force distance characterization. I'm really grateful to Professor Giorgio Bavagliano, who really helped a lot in developing the work done in this thesis and guiding doing many useful issues and providing so many explanations based on solid-state physics, providing how to use stretch exponential equation, and I think many people are going to use this equation after the thesis. I'm also very grateful to our colleague Ashia Wang. I did not find her picture, unfortunately. She did actually the FTIR and XPH data. For my colleague at Ohio State University at NABB, I'm really grateful to Dr. Manu, those two dogs there, Dr. Hongo, where they give me a lot of training for this adhesion and friction measurements, because the calibration for these techniques is really horrible, and they really are expert in this field. I'm also very grateful to the secretary, Katrina, who corrected the English for all the papers we have written, so thank you very much for this. From here, yes, actually, I'm grateful to so many people. It was not possible to post a picture of all, actually, so I selected really some of them. I'm really grateful to Laurent Posqueron for the deposition of PECVD. Many samples we had deposited in a very short time. I'm really grateful to Christina, of course, for fabricating many music devices, for helping a lot, for giving many advices, for David, for Samuel, for Pierre-Francois, and finally for Nicolas Moura for the measurements. I hope that I not forgetting the guy, but that's it. Thank you very much for your attention. 10 minutes more. I'm sorry for this. If it is longer than usual. Thank you.
So I'd like to thank all the people from outside. They did a long trip only to come here, and it was very nice of you for sharing the discussion on these interesting topics. So I will ask the viewers to start the discussion. So starting probably by the grid, is going from north, so okay, so we have the priority, so
Okay, thank you. Thank you for this very nice presentation.
Thank you.
I must say I'm really impressed by the thesis. It's very nice, a lot of original work. I really learned a lot. You also did a lot of work. Impressive. And also thank you for adding one more flavor information to the list.
I'm sorry, I was planning actually to propose a solution, but I needed more for the mechanism.
It's one I didn't know yet, so it's really going to get. Okay, I have some questions. One of the failure mechanisms you mentioned somewhere, but you didn't go into detail, is
Yes.
that you can have charging without having contact. You
Yes.
mentioned field emission or maybe like air gap breakdown. Can you comment on that? Have you ever seen it happening? Have you evidence that it happens?
Yeah,
Or do you think it's not an issue?
it is an issue. I was planning actually to investigate this stuff for contactless charging, but there was no time for doing this. But this is really important because what I have seen from this measurement is that, and you can control this actually, is that you can make your tip actually far from the surface for a determined separation. So I can say 10 nanometer, 20 nanometer and so on, and then I can measure the end-user charge. So I have not investigated this, I'd like to, and this could be done using Kelvin probe Fluorescent microscope. It cannot be done using FDC, it could be done using Kelvin Fluorescent microscope.
So you did not really put in contact?
You control this actually, because in tapping mode, what happens is you are touching the surface, but in fact you are not touching the surface. You are touching it with really very small force, which leads to you to, at the end to, because the force is really very small, you don't touch it. And this is actually verified by the experiment of the effect of the FN tip, because the voltage applied to the tip sometimes reaches 30 and 40 volt, but because of the very short contact time and the very small force, it is really not in contact. So we can do it using this way. But I'd like to do this.
And you think in real MEMS devices it might be an issue?
Yes, because actually in MEMS switches is the case. We have this topography stuff, you have the roughness of the under layer. So of course you have air gaps, and this air gaps is really very small. It's in nanometer. The initial gap actually is like 500 nanometer. With such a small gap, the gas discharge is zero. We have seen this clearly comparing the nitrogen and air. Because what we did comparing this nitrogen and air might be answer this question. At the same humidity, with different gases, we have different charge injections. This, of course, comes from this non-contact charging. But I have not investigated this.
Oh, that's the same conclusion we made, but we never really proved.
Yes, I have read all few papers. Actually, I have done this study based on reading your article. So, yeah.
Another question, you always mention charge density. When you inject charges,
Yes.
how do you control density? Because as far as I know,
Area.
you inject a certain current.
Sorry?
If you with a tip,
Yes?
how do you calculate density from?
Yes, yeah, I go to the point. Actually, we have not calculated the injected charge density. What we have shown here always is the integral of the surface potential profile, and this is an indication of the injected charge density, but this is not the injected charge density. Yes, here. So what we have here, let's say it,
You have it in the beginning somewhere.
I think it is
26 there is a charge density.
yes. Okay, this one. So here actually what we have when we say injected charge density, this is not the really injected charge density. This is just an indication of the injected charge density. We have not calculated that. The integral of the surface potential profile can give you a direct indication of this. As far as this is really high, this means you are injected more charge in your electric, and this results in inducing higher surface potential. So this is not the injected charge density. This is an indication of the injected charge density.
Like the integral is taken over the surface.
Yes.
So it's not over the depth of the
No, it is over the surface only. Yes, actually this is a very important point, because up to now, Very important question in MEMS dielectrics actually is the distribution of the charge. Is it surface or it is body? Here actually we believe, we are not sure, we believe that we are measuring mainly surface charge. Okay? But if we need to go in this in details, we need to make some sort of modeling for Kelvin force microscope to see really what is the distribution of the charge at different depths of the electric. This is one of the points we planned to do a long time ago, but this is really very important issue.
So it's also the question I had here, if you could get information
Yes,
on
yes.
the depth of the charge
Yes.
from these methods or something.
Yeah. It should be very interesting to do. Yeah, I want to write this down.
Another question I had is when I was reading, you mentioned somewhere, because your charges collected at the alternator.
Yes.
You say that they have charge trapping, emission, and also you mentioned percolation.
Yes, yes.
What do you mean with percolation?
Yeah, this is, I think the best guy to answer this is George because this actually comes from his side. I'm going just to I actually asked this questions many times because there is this question is really interesting. I asked George many times. He explains this many times to me. I believe I did not understand carefully. But the point here is, as far as I know from percolation as a concept is divided actually from the fluidics moving in amorphous interfaces. This was actually, I think, 50 years back, where they want to model if you have a liquid coming through an amorphous material, how it will move inside this. So, based on this percolation, there is a percolation theory, which is a mathematical model, okay, a standard model for a disordered system, to explain how your charge is moving randomly through an amorphous material, which is in the case of our dielectric film. This is my understanding. So mainly it is a mathematical model to describe how the charge is moving in amorphous or solid dielectrics. Might be George give, of course, better identification for this.
Yeah, because I was thinking there's a regulation model also to describe the Gaussian dielectric.
Yeah.
I think that's something.
I don't know if it is the same or not, I don't know. But actually percolation is in everywhere, in physics, in chemistry, and fluidics or so.
Yeah. Maybe with the related question, so you study injected charges, so the charges get trapped in the traps. The question I had also is, during your measurements, when you stress the dielectric, are you also making new traps? Or do you assume that the trap density is constant?
We do not assume that the trap density is constant, because we might have also, created traps from this stressing, but based on the measurements we have, we cannot identify really if this comes from the stressing of the material or it is originally inside. I think for this, you might go for deeper characterization techniques for the bulk of the material, mainly TSDC, which can give you an indirect information for this.
Suppose you would stress the trap and then stress again.
Yes.
Are you going into higher values of your injected charge?
I think it depends on the trap energy. It depends on the injection time. It depends on the electric field.
You never tried it?
No.
Could be interesting.
Could be a very interesting point to do this. Yes. Thank you very much for this recommendation.
So you need another
Yeah. I think we need a lot of work to complete this.
If I'm allowed one last question.
Yes.
Okay. Do you believe that we can actually ever solve the problem? Because as far as I know, you can reduce charging in dielectric now, you can play tricks by making it difficult, making it perfect. I can make you in a very good environment, but
Yes.
you will always still have charging.
Yes.
So, do you believe that we can ever make a capacitive switch that is reliable, or should we go to switches without dielectric?
But even with the switches without the electric, we still have other problems like substrated charging. So this is my personal feeling. It's not really. I'm not really optimistic for this problem, because really the point is, as far as you go deep, you discover that you know nothing. And this is really happens with me many times during this study. So I believe that removing the electric is a very good solution. I like this solution from Dimian very well. but still, we don't have an electric network, we have a substrate, we have to solve this problem. So I do believe that the key issue in deriving the switches is electric field. So the message here is to try to use a very small electric field, actuation voltage mainly, to derive this. It has so many problems, of course, like this is small voltage, but as far as I know, without such a solution, of course you can do good packaging to remove the charging and so on, but you have to reduce the cause of the problem, because the charging will happen even if you optimize the electric, even if you increase the gas ratio to reduce the charging or to do all of this, still you will have the charging, because this is done for only 1 second injection. You can imagine this? If you go for like 5 minutes or 10 minutes, which is really short, comparing to the real device, I have this somewhere, but the decay time constant increases very high and the injected charge density increases very high. This is for only, I investigate up to 30 minutes, which is very short compared to the real time. So I believe we have to live with it, because we will never be able to overcome it. And the origin for this is electric field and stress time. So this is my personal feeling.
Thank you.
Thank you.
Okay, thank you.
Thank you.
Thank you very much again.
Yeah.
Okay.
So I would like to first to thank my colleagues from us for inviting me to report on Nobel. Well, I spent a lot of time on reading the thesis, and because I started and I said, well, it's going to take time. So there is so much there, and you did really, I think, really very good work, and this will be a milestone on the
Thank you very much. I appreciate it.
there is a lot, as you said in the end, that a lot of macroscopic phenomena you could explain in the nanoscope.
Yeah.
So that was very interesting. And what I like very much in this work is that you always compare what you get with your AFMT more or less modified with microscopic results on
Yeah.
switches.
Yeah.
So this is really giving a lot of strength to your
Yeah.
work. So I still have many questions, but I will only pick up a few. Okay, what was that? I have one or two things I don't understand. But on the Vugraph 19, which is not that far from here, it's very basic, but from the measurement that you take, yes, you have nanonewtons. While
You
for
mean
me
that
this
is-
is relating to a surface, so it should be a pressure, not a force.
I got this point.
And is there a way we can relate that to a pressure, an electrostatic pressure,
It means contact force? Contact force? Like contact
Yeah.
force?
with a pressure, not a nanonewton? Because it's a nanonewton on what? On 1 pixel or?
Yeah, this is a. Just to verify I understand the question well. Well, let's see how we did this first. What we did actually is we scanned this area. This is 10 micron, right? So we came to a square which is 5 micron by 5 micron, and then we scanned with the FM tip with a specific
force
force.
at the AFM,
I'm sorry?
and the nanonewtons are the force at the AFM.
This is another thing. What we did many things. Well, let me give it one by one. The first thing is we can charge in 2 different ways. The first way is just to go with the FM tip and then scan it line by line. With this, you can control the contact force during charging. Because simply what you have with the FM tip is in contact mode. This is in contact mode. So you come and you touch the surface. And actually, before touching the surface, there is a parameter you define called TM deflection set point, where you're asking the system to have a specific contact force between your tip and the surface. So I might touch it like this or like this. Okay? This is number one. When you start scanning, actually, because of the electrostatic force difference, because you have a biased tip, this contact force increases, right?
Yeah.
There is another option where you can control the contact force of electrostatic could be cancelled during this exchange. Because an important issue here is, if you inject using contact force, you have different charging. Because actually, you can imagine simply that the apex of the tip is changing. So you have different charging areas and time and so on. This is the first message. So you can control the contact force. But what we measure after scanning this area, we're in line by line, or also we can scan it like this. In some cases, we scan it like this. In FDC, thin film, and MEM, we did the same. We do force distance curve all the time in different places while we are charging. And then, actually when we do like this, we charge. When we go up, we measure the induced adhesive force. So what we measure actually is not a pressure, it is adhesive force, because we go with the FM tip with a defined contact force, but then we start to pull the tip up. Pulling the tip up actually is the adhesive force required to pull it up. So it is a force.
I understand that maybe it's not easy, but any idea of the surface which is involved in the contact?
I don't understand the question.
When you start to go down with the IFM tip,
Yes.
What is the contact area?
yes, there is a contact area.
Actually,
It's not zero.
yeah, of course it's not zero, it depends on many parameters. One of them is the apex of the tip. The apex of the tip we have used in this study is around 10 nanometer. This is the apex of the tip. But if you give more force, actually, you have more area. I don't know exactly what is the real contact area between poles.
Can you
But
use-
using Hertzian